We never tried so hard to be superheroes. Okay, we're looking at the properties of capacitors in circuits, but with resistors. So we're going to call these RC circuits here, the resistor capacitor circuits. So let's take a look at this. Let us set up a circuit with some EMF here, some voltage source, a resistor, and then a parallel plate capacitor. Okay, so here's resistor R, here's cap C. We haven't seen this yet. We haven't seen a resistor with a capacitor, and this is very much an AP Physics C concept. So let's do this idea, because we're going to need some calculus here, but let's set up with what we know already. Let's set up a Kirchhoff loop, okay? If I set up a Kirchhoff loop, what are my voltage drops as I go around this in this direction? Starting here behind the EMF, I'm going to have an EMF minus IR, and then minus, and then what's the voltage drop of a capacitor? Well, that voltage drop is equal to Q over C. So minus Q, and in this case, I'm not going to use a capital Q. I'm going to use whatever charge is on the capacitor divided by the capacitance, and this will equal 0. And the reason why I'm doing this is when you start this circuit for an uncharged capacitor, so when time is 0, you are just going to be charging this. So it's going to have some charge Q on it. But then later, it's going to have a different charge Q on it. It's going to have more charge. So this is some charge as a function of time. So I'm going to place this as Q over here. What we really are talking about is Q of T, and that'll come back up right at the very end here, okay? Now, if I want to figure out how does this charge as a function of time, how does that change? How does it increase? How does it decrease if we're charging or discharging a capacitor? What could I do here? Well, now that I've started with this Kirchhoff loop, I can start just diving into some of the heavy mathematics. And what I'd like you to do real quick is I'd like you to think about, from a calculus perspective, how we could rewrite this equation here so that we have a differential piece of a charge inside of it. Okay, so pause the video, think about that for like 30 seconds. Maybe you'll come up with it, maybe you won't. Either way, you'll hit play on the video and we'll get somewhere else. So boom, go do it. Okay, you unpause the video, way to go. So here's how we'll do this. This is a little weird. What we're going to do is we need to recognize that this current here is the movement of charges. It is the movement of charges in some amount of time. And as that current is going around, it is applying charges onto the parallel plate. So we could rewrite this equation like thus. We could say that the EMF minus, and since they're differential pieces, we could say that this is like dq dt. This is the current here. That is the current. Multiplied by some resistance minus Q over C equals 0. That's the little calc move right there. Okay, that's the calculus there. And from here, it's just running with this calculus and understanding how to solve for differential equations, and then pulling a little bit of physics tricks to get things to look pretty in the end. Okay, but this was the move right here. From here, let's take an idea of how can we kind of rearrange things to make them look a little nicer. Well, the first thing I'll do is, it's very common when you're looking at differential equations to try to get this term by itself, okay? And this dq dt, dq is a variable, dt is a variable, you can think of them like that, but we're gonna try to keep them together for the moment. So let's divide everything by r. So we're gonna have an EMF over r minus dq dt minus little q over rc, okay? And this will equal 0. Now, I want to try to make the denominators look the same between R and RC here. So it'd be nice if I could just multiply by 1, saying like C over C here, so my denominators look the same. And what I may recognize then, and this is the physics trick here, is that a capacitance multiplied by an EMF, or a capacitance times a voltage, is the amount of charge on a capacitor, and that's the maximum amount of charge a capacitor could have. So this Q here is different from this little q here, because big Q is the maximum amount of charge the capacitor could have. The little q, as we recall, is that charge at some position or at some point in time. So I can rewrite this equation as saying Q over RC minus dq dt minus little q over RC equals 0. And this is a nice spot for me now. What I'm going to do here is I'm going to recognize that these denominators are the same, so I can link big Q and little q together, and then I'm going to move the negative dq dt over to the other side. So what this will look like is I'm going to pull RC out, so 1 over RC I pulled out, times big Q minus Q, so that's just these two terms right here, there's the minus, and then the dq dt goes on the other side, so this equals dq dt. And what we have here, this is what's referred to as a first order differential equation. Okay, it's a first order because we only have a first variable or first differential here. It's not like the second derivative, but we can solve this first order differential equation pretty easily. It's pretty straightforward, but you do need to know a little bit of calculus in order to do this. What we're going to do here is we are going to separate the variables into their like terms. So we notice here that I have the derivative with respect to time of Q. Okay, these are the charges I'm adding on from the current. I need to get that to link up with this Q here. Okay, those are the same variables that we're looking at here. Unfortunately, because this is actually contained in parentheses, I'm going to have to bring the entire thing over. Makes life a little pain in the butt, but that's okay. Furthermore, this dt, I'm looking for time components to link that with. Well, if you look, there's not a single time in this equation, so it's just going to be by itself, and we're going to put it with other constants that we have. Well, the constants that we have are the resistance and the capacitance. So what we're going to do is we're going to swap sides on this, and we're going to have dt over RC. I just multiplied each side by dt. So there goes the dt, it's over here now, equals, and I'm going to divide each side by q minus q. So it's going to equal dq over the quantity q minus q. Okay? And at this point, we need to start doing some calculus and some algebra here. Okay? So at this point, how do we solve for this? Well, if we're familiar with calculus, we could notice here that we need to integrate these terms here. Okay, and we're going to integrate our left side from bounds starting at time equals 0 to some time later. I don't know what it is, let's just call it t. On our left side here, we're starting, in this case, let's charge the capacitor. So we're starting from some initial charge 0, and we're charging to some charge q later. And in reality, this is the q of t term we're thinking about. So if we take these integrals here, the one on the left is pretty straightforward if you've been taking calculus. The RC get pulled out of the integrand, and it's just the integral of dt, which is t. So we're going to get t over RC on the left side, and on the right, we need to be a little careful here. On the right-hand side, we've got dq over the quantity q minus q. Well, this is a use of the substitution method. So let's set u equal to q minus q, and that means that du is going to be equal to, well, this capital Q is a constant, so when we take the derivative of that, it's nothing. And this q here is something we take the derivative of, because this is q of t, right? So we're going to get minus here, and that's just going to be minus dq. Well, I don't have a minus dq here. I only have a positive dq. So what we'll have to do is multiply this by -1, and since we do it to this side, we'll have to do it to the left side as well, which means that when we carry this negative down, we're going to have a negative down here, so negative t over RC. Now we can rewrite this integral as the integral, and we'll talk about bounds in a second, but this is going to be negative, well, excuse me, that's not going to be negative. The negative from before is going to get locked into this du term, so it's going to be du over u, which is a very familiar integral with calculus. Now, some people like to change their boundaries based off of what they've done for the u. Personally, I just like to flip them back at the end, so however you like to do boundaries here is fine. I'm going to leave my bounds as 0 to q. Math departments will get mad at me at that because I'm technically in dq and those don't apply, but we'll flip them back in the end and you'll see what I mean. Okay. Now, the integral of du over u is one that we should know, and it is the natural log of u. And that's something that you just need to know there. And what we'll do is once we get that natural log of u, we're going to put back in what we actually had for u. We're going to put back in the q minus q value. Okay, and that's why I don't change my bounds because I'm going to dump things back in these terms anyways. So let's write this out here. What we have is negative t over rc, and this is going to equal the natural log of q minus q, and this is bounded from 0 to q. And what this means is that I need to take the top term and plug it in for q, and then I need to subtract the bottom term in from q from that quantity. So the way this will look is the natural log of q minus the top term q minus the natural log of, well, q minus 0 is just the natural log of q. So what we have now, and we can start to see that this is getting a little bit long in the math, but we can do it. Negative t over rc equals, and I need to remember that when I have subtraction of natural logs here, or of logs, we have log rules, I can say this is the same as division. I can divide these. I can say this is the natural log of q minus q over big Q. Okay, and that's a very nice thing to set up there. What I can also do at this point is if I want to get rid of this natural log, I can exponentiate each side. I could say that, hey, look, I'll take an e to the power here, an e to the power here. That caret's how it would look on your calculator. But in this case, when we take the exponential of the natural log, these are going to go away. They're inverse functions of each other. They're going to move each other away from that. Or rather, I shouldn't say functions. They're inverse bases. So what we're going to have now is, let's find a new color. Let's go back to black. We're going to have e to the minus t over rc, because that's the power, equal to q minus q over q. And I could also write that as 1 minus q over q. Okay. If I have this now, I can just clean this up a little bit with some algebra. I'm going to move the q over q over to the other side, and I'm going to bring the e term over, just with addition. So I'm going to have q over q equaling 1 minus e to the negative t over rc. And then what I'm going to do is I am going to multiply each side by this q here. And when I multiply each side by the q, remember, I'm multiplying by the entire term here, I'm going to have the final equation. And the final equation will look like this. It will say that q of t, the charge on the capacitor as time is ticking, so as a function of time, will equal the total charge available on that capacitor multiplied by 1 minus e to the negative t over rc. Now, there's a few interesting things about this. We know that exponents need to have no units according to them. So if this is seconds up here, this means that r times c actually has units of seconds. And as such, we call this a time constant. We call this RC a tau value. So it's a time constant there. Resistance time capacitance is actually a time. Kind of weird. The other neat thing we see with this is if we were to graph this here, if we were to graph the charge Q as a function, oops, excuse me, that's wrong, charge Q as a function of time, what we'd see is if time is 0 here, e to the 0 power is 1, 1 minus 1 is 0, we're going to start this graph at 0. But as time ticks out, and it's nice to do this till time hits infinity, when time hits infinity here, e to the negative exponent here is really like saying 1 over e to that number. So 1 over e to the infinity is essentially a 0, which means e to the 0, well, 1 over e to the infinity is 0, and 1 minus 0 is just 1. So what's going to happen here is our graph's actually going to look like this. And as time approaches infinity, the charge we're going to have here is just big Q right here, because it's just going to be Q times 1, because we're going to have Q times 1 minus 0, and that's all we're going to have there. Okay. If we were discharging this capacitor, and the discharge is a little bit different, the discharge circuit setup is actually just a resistor and just a capacitor to do this. So the Kirchhoff loop looks a little different, but if we were to set up a discharge equation here, the discharge equation is actually going to be that the charge on the capacitor as a function of time is just going to equal Q times e to the minus t over rc. This is for a discharge. Okay. What this would look like in our graph here is you would start at some charge Q, and then as time went out to infinity, you would approach but never touch that x-axis there, okay? So you'd have these charging rates here as given by the RC in the circuit, that time quantity. So these are really the two equations you need. Right here, Q of t equals Q times 1 minus e to the negative t over RC for a charge, and then Qt equals Q times e to the negative t over RC for a discharge. And these are what the graphs will look like there. Sometimes the AP test, they ask us to go through all of this math and solve everything and set up that differential equation, which if you're thinking about the word differential equation, you should be thinking about Kirchhoff loops. That's needed in this type of problem. If you don't set up a Kirchhoff loop, you're dead in the water. But hopefully as we do these a few times and you do some examples, you start just recognizing what the solutions need to be. Boom, boom, and you can quickly make your way through this without dealing with all of the nitty-gritty algebra, without dealing with all of the clever little physics tricks we did here. You can just kind of set things up and be like, boom, I know what the answer is, I know what the graphs look like, I'm a champion. Okay, so that's what's going on here. It's nothing too insane, except we're dealing with a lot of calculus at this point. Okay, so with that, that's the basic idea of how you can set up a charging or a discharging RC circuit, and how you can derive the equations that go along with them and what they will look like in some sort of charge versus time graph. Okay, there's a bunch more AP Physics C, E, and M free response questions that deal with this that I've done. So check out those videos to get some more practice with this and see how we can use these ideas in different problems. But for right now, we are finished. So adios, take it easy.